Hello everyone, welcome to EnviroPioneers. This video is continuation of thermal infrared remote sensing. In part 1, we explored the basic concepts of the thermal remote sensing where we learnt about the kinetic temperature and the apparent temperature, thermal infrared atmospheric windows, thermal radiation laws and the emissivity. In this video, we will learn the concept of thermal properties of the terrain, thermal infrared data collection, thermal infrared environmental consideration, and the application of the thermal infrared remote sensing. So let us start with the thermal properties of the terrain. When we do thermal infrared remote sensing, the primary objective of the temperature measurements and related thermal responses is to infer something about the nature of the composition and other physical attributes of the materials at the Earth's surface or in its atmosphere. All objects on the earth, whether it is water, rock, soil, vegetation, or the earth's atmosphere, they have the ability to conduct heat directly through them onto the another surface, or they have the ability to store heat, and some materials respond to changes in the temperature more rapidly or slowly in comparison to the others. So these ability of the materials are related to their properties like the thermal conductivity, thermal capacity and the thermal inertia. And it is very important to understand these thermal properties because they play important roles in governing the temperature of a body at equilibrium with its surrounding, and they also have an impact on our ability to remotely sense thermal information about various types of materials on the earth. So we will learn about these properties in detail one by one. So first is the heat or thermal capacity. So this is the measure of the ability of a material to absorb the heat energy, and this thermal capacity is defined as the amount of heat energy required to raise the temperature of an entire object by 1 degree Celsius or Kelvin. And the SI unit for the thermal capacity is the joules per Kelvin. This thermal capacity or heat capacity is an extensive property, means it depends on the object's mass and the material's composition. Thermal capacity can be calculated using these two formulas. In the first formula, we have Q divided by delta T. Q is the heat energy added and delta T is the change in temperature. So, this is for the entire object. And likewise, in the second formula, here we have m into C. M is the mass of the object, while C is the specific heat capacity of the material. Now, this specific heat capacity is defined as the amount of heat required to raise the temperature of 1 kg of material by 1 Kelvin, and the unit is joule per kg per Kelvin. So when we multiply the specific heat capacity with the mass of the object, we get the thermal capacity, that is the amount of heat energy required to raise the temperature of the entire object. In this table, we have the specific heat capacity of different substances on the earth. We can see water is having the highest heat capacity, 4184 joule per kg per Kelvin, which indicates that to raise the temperature of 1 kg of water by 1 Kelvin, we will be needing 4184 joule amount of heat. The high value of thermal capacity, as in the case of water and moist soil, it indicates that the materials can store more heat and it leads to slower temperature changes, as we can see in this illustration. Here we have the empty pan. When it is heated, it heats up quickly. But when the same pan is filled with the water, so it does not heat up easily because the specific heat capacity of the water is much high. Likewise, low value of the thermal capacity, as in the case of the rocks, dry soil, and the dry sand, it indicates that the materials do not store heat well and they heat up and cool down quickly. Next, we have thermal conductivity, which is related to ability of a material to transfer heat through conduction, and unit is watt per meter per Kelvin. So, this thermal conductivity is defined as the rate at which heat passes through a specific thickness of a substance. So, it is measured as the number of calories delivered in 1 second across a 1 centimeter square area through a thickness of 1 centimeter at a temperature gradient of 1 degree centigrade. Here we have more simplified representation of the same. It mentions that the thermal conductivity is measured as the number of calories that will pass through 1 centimeter cube of material in 1 second when two opposite phases are maintained at 1 degree difference in temperature. For example, here we can see the temperature is 1 Kelvin and here the temperature is 2 Kelvin. So when two opposite phases are maintained at 1 degree difference in temperature, or we can say that there is the temperature gradient of 1 degree, in that case the rate at which the heat pass through the specific thickness of the substance is defined by its thermal conductivity. Here we have different earth features or the materials along with their thermal conductivity and the specific heat capacity. So the high value of the thermal conductivity, as in the case of the quartz and the granite, it indicates that the heat moves quickly through the material and there is smaller surface temperature fluctuations. While the low value of the thermal conductivity, as in the case of the dry sand, air and the peat, it indicates that the heat transfer is slow within that particular object, and due to this reason the surface temperature fluctuation will be large throughout the day. In case of the soil, moisture content, porosity, density, and mineral composition play a very important role in determining its thermal conductivity. So, as it is mentioned here, that moisture content is the most important factor in the soil because water conducts heat approximately 25 times better in comparison to the air. Likewise, porosity and density, these reduce the conductivity because air in the pores is the poor conductor. Likewise, mineral composition also matters because if the soil is rich in the quartz, it will be having the higher thermal conductivity. Next, we have thermal diffusivity that is represented by small k and is a measure of the rate at which heat is transferred within the substance. So, this thermal diffusivity can be calculated using this formula where k represent the thermal conductivity, rho represent the density, and capital C represent the thermal capacity. So, to understand the thermal diffusivity, let us consider a scenario. Suppose if we are having the two blocks, one of metal and one of wood, and if we are heating one side of each of the blocks, because the metal it is having the high thermal conductivity, it will quickly transfer heat to the other side. But the wood which is having the low conductivity, in this heat will move slowly. But among the materials which are having the same conductivity, the one which is having the lower thermal capacity or lower heat capacity will have the higher diffusivity, means it will heat up and cools down faster. Thus, thermal diffusivity measures how quickly a material responds to changes in temperature, that is, how fast heat spreads through it. So, on this concept, for the objects on the Earth's surface, we can say that the thermal diffusivity governs the rate at which heat is conducted from the surface to the depth in the daytime and from depth to the surface in the nighttime. So, in the materials which are having the high thermal diffusivity, heat waves travel faster and the surface temperature adjusts quickly to influence of the atmospheric condition, while in the materials or the objects which are having the low thermal diffusivity, there is slow temperature adjustment, means deeper layers they remain unaffected by the daily temperature cycles. And as we know that water has high specific heat, therefore minor changes in the moisture content have significant effect on the thermal diffusivity of the soils. Next, we have thermal inertia that defines the resistance of a material to temperature change due to its combined thermal properties like the thermal conductivity, density, and the specific heat capacity. So, this thermal inertia can be calculated using under root of thermal conductivity into density into specific heat capacity. So, this thermal inertia is the measurement of the thermal response of a material to temperature changes. So, those materials which are having the high thermal inertia, for example, water, moist clay, dense bedrock, bedrock, they have the slow response to heating or cooling, and they show a small diurnal temperature variation. But the materials which are having the low thermal inertia, for example, dry sand, snow, vegetation canopy, they show quick temperature response and have the large diurnal temperature variations. Thermal inertia of different objects or the materials on the earth cannot be determined by the remote sensing method because as this parameter depends on the conductivity, density and the thermal capacity which have to be measured in situ by the contact method. But it is possible to remotely sense and compute apparent thermal inertia per pixel. For this, a thermal infrared image is acquired over the same terrain in the nighttime and in the early daytime. And these two images are geometrically and radiometrically registered to one another. Now, for the same place, we have the thermal imagery for both nighttime and the daytime. So, we can calculate the change in temperature delta T for a specific pixel. And it is determined by subtracting the nighttime apparent temperature from the daytime apparent temperature, and apparent thermal inertia per pixel can be calculated using this formula 1 minus A divided by delta T. So this delta T is the change in temperature for a particular pixel, and this capital A is the albedo or the reflectance which is measured in the visible spectrum during the daytime for the pixel of interest. So this thermal inertia, it have an inverse relationship with the measured temperature change. So a high delta T value, it is associated with the terrain materials which have the low thermal inertia, while the low delta T value is associated with the terrain materials which have the high thermal inertia value. So, in a thermal image, areas that have the homogeneous or heterogeneous apparent thermal inertia, it is used by the geologist and the scientist to distinguish the boundaries between the bedrock and the alluvial material, or to discriminate among the rock units with the similar spectral properties, and to identify the zones of the hydrothermal alteration. Now, coming to the next subtopic, that is thermal data collection. So, on the basis of the wavelength range selected for the thermal remote sensing or the time of acquisition, we can have different modes of the thermal data acquisition. Here we have the broadband versus multispectral mode. So, for the broadband thermal sensing, in general, the 8 to 14 micrometer atmospheric window is utilized. But some of the spaceborne thermal sensors, they operate in the wavelength range of 10.4 to 12.6 micrometer, so that ozone absorption peak which is located at 9.6 micrometer can be avoided. So these multispectral thermal channels, these are used mainly for the geological applications. Then we have the daytime versus nighttime acquisition. So this thermal data can be acquired during the day and during the night. For some applications, it is useful to have the data for both the times, but for many applications, nighttime or more specifically pre-dawn images means the data which is acquired before the sunrise are preferred, as during this time the effect of differential solar heating is the minimum, and the platforms for such data acquisitions range from the satellites to aircrafts to the ground-based scanners. So, this thermal remote sensing data can be collected by using the radiometers or scanners or the charge coupled device detectors. So, the most basic instrument for the radiant temperature is the thermal radiometer, which gives us the quantitative information of the energy emitted in the thermal IR range. And this non imaging device measures the radiant temperature using the detectors which are sensitive to electromagnetic radiation having the wavelength range in between 8 to 14 micrometer. Next we have the scanners. These are the imaging devices which can be used in both aircraft or the spacecraft. Any airborne thermal scanner system consists of three basic components: an optical mechanical scanning subsystem, a thermal infrared detector, and an image recording subsystem. These thermal scanners are generally across track thermal scanners, and within these, Deadless DS1260, DS1268 and airborne multispectral scanner are used as the thermal infrared multispectral scanners. These scanners provide most of the useful high spatial and spectral resolution thermal infrared data for monitoring the environment. This DS1260 it records the data in 10 bands including a thermal infrared channel from 8.5 to 13.5 micrometer. This DS1268 it incorporates the thematic mapper middle infrared bands. So here we have two range 1.55 to 1.75 micrometer and 2.08 to 2.35 micrometer. The airborne multispectral scanner contains a hot target thermal infrared detector that detects in the range of 3 to 5.5 micrometer along with the standard thermal infrared detector that detects in the range of 8.5 to 12.5 micrometer. As we saw that airborne thermal scanner system consists of three components. First is the scanning system, second is the detector part, and third is the recording subsystem. So here we can see this is the scan mirror which is rotated with the help of motor, and here we have one hot calibration source. This is the cold calibration source. Here we have the focusing mirror. Then this is the detector which is attached with the help of the liquid nitrogen. Then we have the amplifier, and here we have the high density magnetic tape. Here we have the modulated light source, and this is the optical film recorder. So the scanning system it scans the earth across the track, means perpendicular to the flight direction, and the diameter of the area covered on the earth's surface it is proportional to the instantaneous field of view and the height at which this aircraft is flying. So during the scanning, the photons of the thermal infrared radiant flux which are emitted within the instantaneous field of view, these are routed to a focusing mirror that focuses the photons onto the detector. In thermal remote sensing, quantum or photon detectors are used as the thermal detectors, and these detectors convert the incoming radiant energy into the analog electrical signal. As you can see, within the scanning system, there is hot calibration source and cold calibration source. So as the temperature of these sources are known, the system calibrates itself using the temperature of the known values. These thermal detectors are along with the liquid nitrogen. So the detectors are cooled to low temperatures about minus 196 degrees Celsius, or we can say minus 243 degree Fahrenheit or 73 Kelvin, using the liquid helium or liquid nitrogen. So cooling the detectors ensures that the radiant energy recorded by the detector it is coming from the terrain, not from the ambient temperature of the object within the scanner itself. As the amount of radiant flux reaching to the scanning system is limited, amplifier is needed to amplify the signal which is generated by this detector. So this amplified electrical signal can be recorded on the high density magnetic tape and can be stored, or a black and white thermal data can be generated with the help of the modulated light source on the aircraft itself. These thermal detectors that are used in the thermal remote sensing are usually composed of indium antimonide with a peak sensitivity near 5 micrometer, or mercury doped germanium with a peak sensitivity near 10 micrometer, or mercury cadmium telluride which is sensitive over the range from 8 to 14 micrometer. Apart from across-track scanners, push broom, linear or area array charge coupled device detectors can also be used. These are the solid state microelectronic detectors which are smaller in size and lighter in weight, and they require less power to operate. And as they have the fewer moving parts, they are more reliable, and each detector in the array can view the ground resolution element for the longer time, and it allows more photons within the instantaneous field of view to be recorded by the individual detector. Thus, it helps in improving the radiometric resolution. And as each detector element in the linear or area array is fixed relative to all other elements, the geometry of the thermal infrared image is much improved in comparison to those produced by the across-track scanning system. Another method of thermal data collection is by using the forward-looking infrared system. As the name suggests, these systems look obliquely ahead of the aircraft and they acquire high quality thermal infrared imagery, especially in the nights. And this forward looking infrared system, they collect the infrared energy based on the same principle as an across track scanner. But there are two basic differences. First is that this scan mirror it points forward about 45 degree, and second is that it projects the terrain energy during a single sweep of the mirror onto a linear array of thermal infrared detectors. If we see the development in thermal remote sensing, in 1978, NASA launched the Heat Capacity Mapping Mission (SCMM), which was dedicated to observe the thermal state of the Earth's land surface. And after this, subsequent sensors with diverse spatial and the temporal resolutions were launched in polar orbiting or geostationary platforms by the National Oceanic and the Atmospheric Administration, the European Space Agency, the European Organization for the Exploitation of the Meteorological Satellites, or various agencies in the China, Japan, and other countries. High resolution observations began in 1982 with the Landsat 4 with the use of the thematic mapper sensor, which introduced a TIR band at approximately 100-meter resolution. This temporal resolution was significantly improved by the NASA's Moderate Resolution Imaging Spectroradiometer, which was placed on the Terra and the Aqua satellites, providing the global coverage 4 times daily via the complementary orbit. Then geostationary advancements followed with the Meteosat second generation introduced multi TIR bands and the temporal resolution of 15 minutes, and these set the standards for the Meteosat third generation. Thermal data acquisition further got improved by the introduction of hyperspectral thermal infrared sensing, which is very helpful in the atmospheric monitoring. It began with the interferometric monitor for the greenhouse gases. Now we have the advanced sensors such as the atmospheric infrared sounder, the infrared atmospheric sounder interferometer, or the cross-check infrared sounder. Once this thermal data is collected from the terrain, it can be processed and displayed as either grayscale images or colored images. So, a grayscale image is an image of relative radiant temperature and it is referred as thermogram, where जो darker shades हैं, these indicate the cooler temperatures, while the lighter tones they reflect the warmer areas. While in the colored images, here we can use the gradient from blue to red, and the blue color indicate cooler areas while the red color indicate the warmer areas. When we have thermal data, either in the form of grayscale image or colored image, interpretation of these images is different from what we do in the optical remote sensing. So here it is necessary to understand the diurnal cycle and its relation to the temperature of objects on the earth surface. So this diurnal cycle means complete 24 hours. If we see in this image, this red line, it indicates daily temperature in the lower atmosphere, means near to the earth surface. And here we have the energy rate. This one is representing the incoming solar energy, and this blue line is representing the outgoing energy in the form of the long wave radiation. So we can see from sunrise to sunset, earth receives the solar radiation in the form of incoming short wavelength energy, and it reflects much of it back into the atmosphere, and this is the portion where we use optical remote sensors, and some of this incident solar energy is absorbed by the earth's terrain and it is emitted in the form of long wave radiation, which is having the wavelength in the range 3 to 14 micrometer, and this we call thermal infrared wavelength radiation. If you notice in this part of the image, Earth receives maximum amount of solar radiation around noon, while the maximum amount of outgoing radiation is around 4 p.m. in the evening. So there is lag of 2 to 4 hours, and this is mainly due to the time taken to heat the soil. During daytime, from sunrise to sunset, the earth receives the incoming solar radiation, and this energy is either reflected or absorbed. So there is reflection of the short wavelength energy and emission of the long wavelength energy, and both of these contribute to the outgoing radiation. So the difference between the incoming radiation and outgoing radiation, it causes an energy surplus to take place during the day. And after sunset, both incoming and outgoing shortwave radiation become zero. But this outgoing long wave radiation exiting the terrain, it continues all night. So the thermal data acquisition can be done both during the daytime as well as during the nighttime. And generally, nighttime is preferred because there is no interference of the shortwave radiation. Now let us learn about the diurnal temperature cycle of typical materials. This image has been taken from the book Remote Sensing of Environment by Jensen. Here we have the typical diurnal temperature variation for soil and rock, vegetation, water, moist bare soil, and the metal objects. There is a point mentioned here that if all of these curves lie exactly on top of one another, then remote sensing in the thermal infrared portion of the spectrum would be of no value because all the phenomena would have the same apparent radiant temperature. There would be no contrast in the imagery between the different phenomena. But if we see in this image, each of the feature they have unique diurnal temperature variation, and there are only two times during the day, after sunrise and near sunset, when some of the materials like the soil rock, vegetation, and water, they have exactly the same radiant temperature. So this time is referred as the thermal crossover, and during this time period thermal data acquisition is generally not suggested. Some materials which have higher thermal capacity, they store heat more efficiently than others. For example, water has a much higher thermal capacity in comparison to the soil and rock. If we see in this image, this bold line is representing the diurnal temperature variation for bare soil and rock or concrete. So here the daytime temperature is much higher, while in the nighttime we can see the temperature is much reduced. So the fluctuation is this much. And for the water, we can see this dotted line is the radiant temperature during night, and here it is for the day. So the diurnal temperature variation is very less. So it is mentioned here for water, the diurnal temperature range fluctuates very little in comparison to the bare soil or rock during a 24-hour period. Suppose if we have two thermal infrared imagery, one is acquired at about 2 p.m. in the daytime and another is acquired at about 4 a.m. in the morning. So, in the daytime thermal imagery, as the apparent temperature of the bare soil or rock it is much higher in comparison to the water, they will appear brighter. And during the early evening, this bare soil and rock or concrete, it is still warmer in comparison to the surrounding terrain. But as these features continue to radiate energy into the atmosphere during the night, their apparent temperature become less in comparison to the water. So in the nighttime imagery, they will appear darker in comparison to the water. As water maintains a relatively stable surface temperature throughout 24 hours, so in the daytime imagery, it will be colder or will appear darker in comparison to the bare soil, rock, concrete, or vegetation. But in the nighttime imagery, water will appear brighter in comparison to other features. As vegetation contains water, it is usually cooler and appear darker than soil and rock on the 2 p.m. daytime imagery and warmer and brighter than soil and rock on the pre-dawn imagery. Vegetation tends to be slightly warmer than water throughout the day, and it is cooler than water during the pre-dawn hours, and very moist soil. It also tends to have a stable diurnal temperature cycle because the more water in the soil, the higher is its thermal capacity. And metal objects, they have very less radiant temperature because of their high reflectivity and low emissivity. If you remember, we have studied that good metal reflectors are poor absorber and therefore poor emitters. Thus, metal objects such as cars and the aluminium rooftops, they appear cool or dark on both daytime as well as nighttime thermal infrared imagery. To compute thermal inertia, scientists require both daytime as well as nighttime imagery. Otherwise, for general purpose, they prefer to collect pre-dawn thermal infrared imagery because in the daytime, short wavelength reflected energy can create annoying shadows, and by 4 am most of the materials in the terrain, they have relatively stable equilibrium temperature. Effect of the wind on the aircraft is minimized as there will be less scrapping of the aircraft, and it results in more accurate flight lines, and there is no wind smears or wind streaks on the imagery. Now, coming to the applications of thermal remote sensing. So, thermal data for a particular area can be obtained from different directions or for different time interval and in different wavelength ranges. There are number of sensors placed at different platforms which acquire the data in thermal infrared region in different spatial and spectral resolution. Once we have the thermal data for a particular area, we can estimate two parameters, that is temperature and emissivity. So these are the direct variables. And using these two parameters, we can estimate other parameters which are referred as the derived variables like the radiation, atmospheric composition, water vapor, moisture, or evapotranspiration. And using these variables, thermal remote sensing can be used in wide range of applications like urban heat island, thermal anomaly, mineral exploration, agricultural drought, vegetation monitor, etc. So we will learn some of these applications in brief. First, we have the use of thermal remote sensing in estimation of land or sea surface temperature. And these are used to estimate urban heat island or the climate studies. Land surface temperature, LST, it refers to the temperature of the Earth's land surface. Likewise, sea surface temperature refers to the temperature of the sea or ocean, and it is the skin temperature of the ground, not the air temperature. And this land surface temperature is very important parameter for broad range of applications related to weather and the climate, hydrology, etc. And it is most widely used in estimating the urban heat island. So these urban heat island occur when cities experience significantly higher temperature than surrounding rural areas, and it is mainly because of the human activities and use of heat retaining surfaces like the asphalt. So the thermal sensors help to map these temperature variations, and it provide the data for city planners to mitigate the effect through urban greening or material changes. And in climate studies, long-term thermal data, it enables the scientists to track trends in the surface temperature, monitor global warming, and assess the regional climate changes. In thermal infrared remote sensing of land surface temperature, sensors provide us these data: top of atmosphere brightness temperature, satellite zenith angle, satellite azimuth angle, land surface temperature, and emissivity of the surface. These data can be used in climate change processes to understand the global warming, interannual climate variabilities, heat waves, and drought, and also in land surface processes to understand the soil moisture dynamics, forest dynamics, general vegetation dynamics, wildfire, snow and permafrost dynamics, urbanization, etc. This image has been taken from a research paper where authors have shown the average land surface temperature of summer day in 2000 and in 2020. So they have compared the land surface temperature of a place over the period of 20 years. Similarly, this image has been taken from another research paper where authors have shown the land surface temperature distribution, and here we have the range of temperature. This section shows LST in 2003, here we have for 2007, and here we have for 2013. And from these images, we can have an estimate that land surface temperature of the study area have increased from 2003 to 2013. Thermal remote sensing can also be useful in agriculture for detecting the soil moisture level and for identifying the plant stress. Here, if you see, in the moist soil condition, we have the high transpiration and open stomata. So, the sensor record low leaf temperature, while in the dry soil condition, there is low transpiration and closed stomata, and the sensor record high leaf temperature. So here it is mentioned that in case of drought or in case of insufficient irrigation, when there is dry soil condition, the plant undergoes increased rate of water loss through its stomata compared to the rate at which it can absorb the water through its root. And in response to this imbalance, the plant modulates the size of its stomatal opening, and this is the mechanism to mitigate the extent of water loss during the evaporation process. And this adaptive response plays a very important role in preventing the wilting and excessive drying. And the degree of adjustment vary depending on the duration and the severity of the stress. So, closing of stomata leads to an increased land surface temperature of the crop canopy, and it can be measured directly via the thermal data. And this water stress to plant can be detected in advance using thermal remote sensing, because thermal remote sensing can detect this stress a couple of days earlier in comparison to the optical data. Here we have the true color composite of the agricultural area, and these are the thermal images for the same. This is captured at 3rd May 2023 10:30 am. It is captured at 11th May 2023 10:30 am, and this is captured at 20th June 2023 10:30 am. In true color composite, we can see normal pattern of the agriculture field. But in the thermal images, some of the patches are having the higher temperature in comparison to the others. So using the thermal data, we can detect the stress before it is visible, and we can assess the impact of the soil cover on the stress. And here we are having the green vegetation, but also we are having the higher temperature data. So it is green, but is it okay? Means whether the plant is under stress or not, we can estimate using the thermal data. And if we see, some of the patch is still having the lower temperature. So under stress condition, which hybrid is able to survive better, we can identify those species. So thermal remote sensing, it provides a direct indicator of water stress, making it useful in the drought assessment and monitoring. When a leaf transpires, it cools relative to the surrounding air, and as water becomes scarce, transpiration reduces and leaf temperature increases. Therefore, water stressed plants, they experience higher leaf temperature in comparison to the non-stressed vegetation. Therefore, thermal images can detect the rising canopy temperature to inform the optical irrigation timing. Thermal remote sensing can also be useful in hydrology for measuring the evapotranspiration and water body monitoring. So, evapotranspiration is the process by which water is transferred from land to the atmosphere through evaporation and plant transpiration. So, monitoring the evapotranspiration helps us in understanding the water uses in ecosystems and managing the agricultural irrigation. Thermal remote sensing can also provide us the data about the temperature changes in the rivers, lakes, and oceans, and this data is essential for assessing the water quality, detecting the thermal pollution, and monitoring the changes in aquatic ecosystem due to the climatic shift. Thermal remote sensing is also used in geology and volcanology to identify the thermal anomalies associated with the geothermal activity or to monitor the volcanic activity. So, the elevated surface temperatures in the geothermal areas or around the active volcanoes can indicate lava flows, magma movement, or the eruptions. So, this remote sensing technology, including the thermal infrared bands, help the geologist to detect and analyze these thermal changes in real time, which provide them crucial data for forecasting the volcanic eruptions and monitoring the health of volcanic regions. Here we have the photographs and the thermal images of the volcano. So using the thermal data, we can have the idea of the intensity and the direction of the magma flow. Similarly, in the second image, here we have the photographs and these are the thermal images for the volcano. The first one is captured at 4th February 2015 and the second one is captured at 7 June 2015. And the colored image of the thermal data provides us the temperature variation at the top of this mountain. Thermal remote sensing is also very important in disaster management, particularly for detecting the wildfires and oil spills. So, thermal sensors can identify the hotspots in the fire prone regions, helping to detect the wildfires early, and it allows the emergency services to respond quickly. And during active fires, thermal images can map the extent and the intensity of the blaze, guiding the firefighting efforts. And in case of oil spills, thermal imagery can detect the temperature differences between the oil and water, helping in the identification of spill and taking the preventive measures accordingly. This is the thermal image of a forest fire. So the color coding we can see the yellow one is representing the temperature around 301 degrees Celsius. Likewise, here we have the conventional RGB images and these are the thermal images. So using the thermal image, we can identify the places where we have the forest fires. Thermal remote sensing can also be useful in identifying the patch within the forest where deforestation has been done. As we can see in the thermal image, in the barren area where deforestation has been done, temperature has increased significantly in comparison to the nearby areas. Thermal remote sensing is also useful in understanding the ice and snow on the earth. Though the ice and snow they have high albedo and reflect a significant portion of the incoming solar radiation back into the atmosphere, but they also emit the thermal radiation which is influenced by their emissivity. So the fresh snow which has high porosity, it displays low emissivity, while the older compacted snow and ice they have the higher emissivity value. So here we have ice and snow emissivity data comparison. On the y axis it is representing emissivity and on the x axis we have the wavelength in micrometer. Here we can see that solid ice is having the maximum emissivity, and in the case of the snow, the coarse granular snow is having the maximum emissivity, followed by medium granular snow, and then in the last we have the fine granular snow. So the factors such as grain size for the snow, bubbles for glacier ice and the lake ice, brine inclusions for sea ice, and surface roughness, all these factors impact the emissivity of snow and ice. So there are wide range for applications of thermal remote sensing. We have covered the basic concept in these two videos. Now depending upon your area of interest, you can explore for particular application in more detail. Here we have compilation of some of the sensors, the platforms, thermal bands and the spatial resolution, their temporal resolution. So there are different sensors for thermal remote sensing. Here we have Landsat, then we have the Aster, MODIS, visible infrared imaging radiometer suite. Likewise, other sensors and their spatial and spectral resolution are mentioned. If you are working in the field of thermal remote sensing, I have also compiled official data sources for the thermal remote sensing sensors. You can visit to these websites for downloading the data. The link of each of the website I will also mention in the description box. So these are the references for the content of this video. Majority of the content have been taken from the book Remote Sensing of the Environment by Jensen, and some of the content have also been taken from these websites. These three are also the official website from where the thermal data can be acquired. If you have any query, let me know in the comment section. We will meet soon in the next video. Thank you and best wishes.